And while he gets set up, our next speaker is Qinghao Hu. He is a research associate at Nanyang Technological University, and he's going to be talking to us about scalable and interpretable scheduling for deep learning training jobs.
Hello everyone, my name is Qinghao. I'm really excited to be here to present our work, Lucid, a non-intrusive, scalable, and interpretable scheduler for deep learning training jobs. This is a joint work with Zhang, Peng, Yonggang, and Tianwei from Nanyang Technological University, Shanghai's AI Lab, and SenseTime. Nowadays, deep learning become ubiquitous. Many enterprise or research institutes build their GPU clusters to facilitate their model development. Users submit various training jobs. These jobs span different domains. They also have different purposes, like distributed training, hyperparameter searching, and debugging. The model execution rely on DL frameworks, like TensorFlow and PyTorch. To manage a large number of DL workloads, there is a cluster scheduler allocate resources to jobs under a scheduling policy in order to achieve some cluster-wide objectives, like the maximize cluster utilization and fairness. To strive for better scheduling efficiency, many novel schedulers adopt some advanced mechanisms. For example, job preemption mechanisms enable pause and resume jobs to mitigate the blocking issue incurred by long-term jobs. And the elastic training is another mechanism that is used to improve cluster utilization by growing or shrinking job resources. And GPU sharing allowed multiple jobs to share the same GPUs to fully utilize the resources. Although existing work have demonstrated significant improvement, there are more barriers and concerns in practical deployment. The most significant barrier is that existing work based on intrusive paradigm. All of these advanced techniques rely on code intrusion, on user script, which require users to manually import specific libraries and modify their codes. Additionally, some works also need to modify the source code of underlying DL frameworks or CUDA library. The intrusive paradigm leads to some fundamental deficiencies. First, users are reluctant to adopt them because of the extra burden and the less flexibility. Besides, the high maintenance cost to adapt fast iterative DL ecosystem is unaffordable for most companies. Moreover, some schedulers adaptively adjust the job bench size and the learning rate to strive for extreme training efficiency. However, this can degrade the quality of the final model. Additionally, the scheduling policy aspects also have some limitations. Existing work commonly adopt machine learning or mathematical solving-based techniques to optimize their scheduling policy. However, developers often ignore model interpretability during system design, resulting in opaque decision-making. And operators cannot guarantee the model predictions are reliable and have sufficient confidence to deploy them. On the other hand, as the workload becomes more intensive, mathematical solving-based policy may take hours to solve a job allocation problem. Therefore, they meet the scalability bottleneck. In summary, barriers to practical deployment fall into two main categories. So, is it necessary to use complex or intrusive approach to achieve efficient scheduling? No. Our work demonstrates that simple non-intrusive scheduling is sufficient. Our scheduling system, Lucid, follows 3 design principles for practical and simple system deployment. First, Lucid requires 0 user effort, 0 framework modification, and follow a preemption-free manner. Besides, the system can obtain scheduling decision remotely for massive and complex workloads. Furthermore, all the modules of Lucid are transparent and intelligible to operators. Different with the existing work that intrinsically inspect job throughput and try job packing. We find that we can proactively pack jobs without introspection. As shown in the figure, we measure the jobs packing effect on RTX 3090 over popular modules. It is evident that even 2 jobs GPU utilization summation reaches 100%. Almost all job pairs still can obtain quite good throughput. This relationship inspires us to make a packing decision based on hardware utilization features. To achieve efficient scheduling, our system optimizes job profiling, packing, and allocation processes. First, jobs need to be profiled before allocation. This step can efficiently filter most short-term debugging jobs. Then the profiler records the resource utilization features and classify jobs into different categories. And we design a binder to determine whether and how to pack jobs. Then the resource orchestrator assign a priority value to each job and select jobs to execute. Besides, we also design a system tuner and update engine for system performance maintenance. In job profiling stage, we adopt an interpretable model based on our previous work, Primo. Specifically, we designed showing score scheme to simplify interference prediction into a tiny classification problem. Namely, we classify jobs into tiny, medium, and jumbo 3 categories with different showing scores. And we only use some non-intrusive resource usage features in like GPU utilization to generate the model. From the trend decision tree model, we can clearly understand how Lucid classify each jobs. Additionally, we perform both the spatial and temporal optimization to improve profiling efficiency. We prioritize jobs with less GPU demand and dynamic adjust profiling capacity and time limit. After profiling and getting job showing score, we design a fine job binder to pack jobs based on GPU showing capacity scheme. It restricts the sum of showing score on each GPU to avoid interference. Moreover, Lucid supports prediction-based dynamic adjustment and prioritize shorter jobs packing to improve scheduling performance. Based on this scheme, we can find over 80% packing opportunities, and the majority of them are interference-free. Our resource orchestrator schedule jobs based on duration estimation. It based on the key observation reported by recent work. Majority of workloads have recurrent patterns, and the users tend to submit similar jobs multiple times. So we assign the job a priority value to optimize the scheduling order. It consists of 2 parts. The first part, we predict the job duration with an interpretable model based on profiled and log features. Besides, we further consider job GPU demand in job priority assignment. In our evaluation, we adopt 3 long-term real-world traces from SenseTime and Microsoft. They have over 10,000 of jobs. We use training workloads from various domains, including CV, NLP, RL, and the recommendation. We perform large-scale simulation based on these traces. The figure shows the CDF of job completion time, and we can see Lucid outperforming trace baselines. We've also evaluated Lucid queuing delay across different virtual clusters. We find Lucid perform stable across the various workload distribution. Overall, Lucid reduced average JCT and queuing delay by 1.3 times and 9.1 times respectively. As a summary, first, Lucid identified the barriers of practical scheduling system deployment. To address this issue, Lucid optimized job packing and scheduling based on interpretable model to achieve efficient scheduling. And our experiment demonstrates non-intrusive scheduling can provide comparable performance to preemption-based schedulers. Our code is open source. Please check our GitHub website. Thanks for your listening. We are happy to take any questions.